Hi everyone, and welcome to my ASMR channel. This is going to be my first video. All my videos are going to be just story related, book related. They're all going to be just reading different stories, different chapters. So today we have a chapter about wormholes and time travel. So let's get started. The last chapter discussed why we see time go forward, why disorder increases, and why we remember the past but not the future. Time was treated as if it were a straight railway line on which one could only go one way or the other. But what if the railway line had loops and branches, so that a train could keep going forward, but come back to a station it had already passed? In other words, might it be possible for someone to travel into the future or the past? H.G. Wells, in The Time Machine, explored these possibilities, as have countless other writers of science fiction. Yet, many of the ideas of science fiction, like submarines and travel to the moon, have become matters of science fact. So, what are the prospects for time travel? The first indication that the laws of physics might really allow people to travel in time came in 1949, when Kurt Gödel discovered a new space-time allowed by general relativity. Gödel was a mathematician who was famous for proving that it is impossible to prove all true statements, even if you limit yourself to trying to prove all the true statements in a subject, as apparently cut and dried as arithmetic. Like the uncertainty principle, Gödel's incompleteness theorem may be a fundamental limitation on our ability to understand and predict the universe. But so far, at least it hasn't seemed to be an obstacle in our search for a complete, unified theory. Gödel got to know about general relativity when he and Einstein spent their later years at the Institute for Advanced Study in Princeton, USA. His space-time had the curious property that the whole universe was rotating. One might ask, rotating with respect to what? The answer is that distant matter would be rotating with respect to directions that little tops or gyroscopes point in. This had the side effect that it would be possible for someone to go off in a rocket ship and return to Earth before he set out. This property really upset Einstein, who had thought that general relativity wouldn't allow time travel. However, given Einstein's record of ill-founded opposition to gravitational collapse in the uncertainty principle, maybe this was an encouraging sign. The solution Gödel found doesn't correspond to the universe we live in, because we can show that the universe is not rotating. It also had a non-zero value of the cosmological constant that Einstein introduced when he thought the universe was unchanging. After Hubble discovered the expansion of the universe, there was no need for a cosmological constant, and it is now generally believed to be zero. However, other more reasonable spacetimes that are allowed by general relativity and which permit travel into the past have since been found. One is in the interior of a rotating black hole. Another is a space-time that contains two cosmic strings moving past each other at high speed. As their name suggests, cosmic strings are objects that are like string in that they have length, but a tiny cross-section. Actually, they are more like rubber bands because they are under enormous tension, something like 1,000,000,000,000,000,000 tons. A cosmic string attached to the Earth could accelerate it from 0 to 60 miles per hour in 1/30th of a second. Cosmic strings may sound like pure science fiction, but there are reasons to believe they could have formed in the early universe as a result of symmetry breaking of the kind discussed in Chapter 5. Because they would be under enormous tension and could start in any configuration, they might accelerate to very high speeds when they straighten out. The Gödel solution and the cosmic string space-time start out so distorted that travel to the past was always possible. God might have created such a warped universe, but we have no reason to believe he did. Observations of the microwave background and of the abundances of the light elements indicate that the early universe did not have the kind of curvature required to allow time travel. The same conclusion follows on theoretical grounds, if the no-boundary proposal is correct. So the question is, if the universe starts out without the kind of curvature required for time travel, can we subsequently warp local regions of space-time sufficiently to allow it? A closely related problem that is also of concern to writers of science fiction is rapid interstellar or intergalactic travel. According to relativity, nothing can travel faster than light. If we therefore sent a spaceship to our nearest neighboring star, Alpha Centauri, which is about 4 light-years away, it would take at least 8 years before we could expect the travelers to return and tell us what they had found. If the expedition were to the center of our galaxy, it would be at least 100,000 years before it came back. The theory of relativity does allow one consolation. This is the so-called twins paradox mentioned in Chapter 2. Because there is no unique standard of time, but rather, observers each have their own time as measured by clocks that they carry with them, it is possible for the journey to seem much shorter for the space travelers than for those who remain on Earth. But there would be much joy in returning from a space voyage a few years older to find that everyone you had left behind but there would not be much joy in returning from a space voyage a few years older to find that everyone you had left behind was dead and gone thousands of years ago. So, in order to have any human interest in their stories, science fiction writers had to suppose that we would one day discover how to travel faster than light. What most of these authors don't seem to have realized is that if you can travel faster than light, the theory of relativity implies you can also travel back in time. As the following limerick says, there was a young lady of white who traveled much faster than light. She departed one day in a relative way and arrived on the previous night. The point of the theory of relativity says that there is no unique measurement of time that all observers will agree on. Rather, each observer has his or her own measure of time. If it is possible for a rocket traveling below the speed of light to get from event A, say the final 100-meter race of the Olympic Games in 2012, to event B, say the opening of the 100,004th meeting of the Congress of Alpha Centauri, then all observers will agree that the event A happened before event B according to their times. Suppose, however, that the spaceship would have to travel faster than light to carry the news of the race to the Congress. Then there would be no relation between the distance through the wormhole and the separation of its ends in the nearly flat background. Thus, no one could imagine that one could create or find a wormhole that would lead from the vicinity of the solar system to Alpha Centauri. The distance through the wormhole might only be a few million miles, even though Earth and Alpha Centauri are 20 million miles apart in ordinary space. This would allow news of the 100-meter race to reach the opening of Congress. But then an observer moving toward the Earth should also be able to find another wormhole that would enable him to get to the opening of Congress on Alpha Centauri back to Earth before the start of the race. So, wormholes, like any other possible form of travel faster than light, would allow one to travel into the past. The idea of wormholes between different regions of space-time was not an invention of science fiction writers, but came from a very respectable source. In 1935, Einstein and Nathan Rosen wrote a paper in which they showed that the general relativity allowed what they called bridges, but which are now known as wormholes. The Einstein-Rosen bridges didn't last long enough for a spaceship to get through. The ship would run into a singularity as the wormhole pinched off. However, it has been suggested that it might be possible for an advanced civilization to keep a wormhole open. To do this, or to warp space-time in any other way, so as to permit time travel, one can show that one needs a region of space-time with negative curvature, like the surface of a saddle. Ordinary matter, which has a positive energy density, gives space-time a positive curvature, like the surface of a sphere. So, what one needs in order to warp space-time in a way that will allow travel into the past is matter with negative energy density. Thank you so much for listening today. I will be back next week with another video. Let me know if you would like me to read more from this book, or, I have other books to choose from, so just let me know in the comments. Thank you so much. Have a great day.